Hello, dear audience. Now I report about our work. I try to say about local dynamics in dendrimers. We know that exist theoretical approaches based on Gaussian model of subchains, and this theoretical approach described local dynamics in dendrimers, but these approaches neglect excluded volume interactions, and these interactions exist in real dendrimers. Dendrimer is regular tree-like branch structure. On left side we see a full atomic model of dendrimers, and on right side we can see schematic representation of dendrimer. Dendrimer have different applications, and for these applications very important to know local dynamics. In experiment, local dynamics study using to measure spin lattice relaxation rate, and on left side we see a full atomic part of dendrimers, and vector B, it is labeled vector in this method, and vector B with index t, it is terminal vector, and with index I, it is internal vector. And upper right small figure, we can see angle. This angle depends on time and measure in this method. And next we can calculate articulation function from this angle, and next we calculate spectral density by using cosine Fourier transformation and linear combination of spectral density. It is spin relaxation rate. In this work, people compare experimental and full atomic data, and how we can see on this figure, we have the same effects, that in inner and terminal vectors have different behavior. And what is reason of this behavior? Before I try to say about theory, I want to say that in experiments people use temperature as variable, and in theory it is frequency, it is variable, but temperature, it is constant. Now I talk about theory of Gaussian dendrimer. This theory have three assumptions, that bonds, it is entropic springs, that excluded volume interaction are neglected, and this model use phantom model, and also in this paper people use symmetry of branching. And main result that if we not introduce restriction on angle between bonds, we have the same position of internal and terminal vectors. But if we introduce this restriction, we have a different position. Maybe it is answer about why we see the same behavior in experimental data, but in real dendrimers we not have entropic springs. We have rigid bond, and the second real dendrimers have excluded volume interactions, and also, for example, within dendrimers have asymmetry of branching. And main questions: will the consideration of risk factors change the theory conclusions? For this task, we use coarse-grained model. In left side, we see representation of coarse-grained model from full atomic model, and coarse-grained model help to change different parameters and see how these parameters influence on local dynamic in dendrimers. We use different potentials, and this potential give us four main models. First models, it is without restriction on angle between bonds. It is flexible phantom model. Next, it is then we introduce restriction of angle. It is phantom semi-flexible model, and also analogies for excluded volume interactions. And we see that if we use excluded volume interactions, we have restriction on angles between bonds in case if we not introduce these restrictions. We use Brown dynamic simulation. We simulation very quickly because we not use solvent molecules. We have we make a numerical solution with equations, and we have full algorithm our calculation. We solve motion of Brown dynamic equations. We get trajectory. From this trajectory, we calculate articulation function, for example, and make cosine Fourier transform, calculate spectral density, and last we calculate spin relaxation rate. In our first question, how influence asymmetry of branching? We consider two models, symmetric and asymmetrical dendrimers, and we see that asymmetry of branching not influence on average size of dendrimers, and we see that asymmetry of branching also can explain effects in real dendrimers, because inner and terminal vectors in these models have the same positions. The second question is how how introduction on restrict on angles influence on the same problem. We see that that if we introduce restriction on angles for excluded volume model, we not have a signification effects. We have the same size of average size of dendrimers, and but for local dynamics we have results that excluded volume interaction not change position of local dynamics of maximum of frequency dependence, and we also see that restriction on angles leads for shifting position of maximum, and it is the same results like in theory. And conclusions. We understand that position of maximal spin relaxation rate for internal and terminal groups for flexible dendrimers have the same position, and this conclusion also true for phantom excluded volume models, and we have the same results like in theory.
Are you finished?
Yes.
Let's thank the speaker for very interesting topics, and please ask questions. Have we got some questions? I think you have
a first question.
You have to ask, I'm sure.
Excuse me, please. It's only a small question. Can you explain me the definition of the correlation function you have given? You have mentioned the average of T2, TP2 from T, but this is not the correlation function in the beginning. Perhaps I have a problem.
On this one?
Yes, this is not the correlation function. This is the average of the Legendre polynomial of second order.
Yes, you're right. Yeah.
Yes, thank you. Yeah.
Okay.
And maybe it's necessary to underline that the author is used not usual relaxation rates, but reduced relaxation rates divided on frequency.
Yeah, it doesn't matter. It's very, very short remarks. But if you have no questions, I'd like to make some remarks. First of all, I have some experience for investigation toward dendrimer, which was synthesized by academician Muzaffarov. Do you know his name? Academician Muzaffarov. And I investigate the diffusion. And from my point of view, we also try to estimate the relaxation rate, but here, because a lot of methyl groups is only methyl group rotator, but cell diffusion is a very good parameter for the estimate of associations and in this kind of. But there is no remarks, no reference on the academician Muzaffarov investigations. I think that you are only on the first way to understand it. But please try to see literature.
A question.
Yes, sure.
Yeah. You mentioned that in theory we investigate the dependence on frequency, and in experiment frequently and usually they use temperature dependence. And
Yes, because the temperature depends, concentration depends.
Compare theoretical and experimental data in this case?
I understand your questions.
Our paper was published in Applied Magnetic Resonance many years ago. I think it will be very useful for you to see this, to read this paper. In order don't show this very not interesting results.
Allow to answer to my question.
Okay. I think we must make many simulations. For each simulation, we
It's only rotating of Bessel groups. The main mechanism of relaxation. I know his answer.
Excuse us.
Yes. Yes. In each simulation, we try to get results for the same temperature, and then we make many points we can compare with experimental data.
But in simulation, it's very difficult to realize the real temperature. It's more or less
Yes,
a hypothesis.
yes, but it is not my task because I make a coarse-grained simulation. It is, I think.
But I mean not simulation, not molecular simulation, but NMR experimental data. How can you compare this, your predictions?
I understand. I not compare quantitative results. I want to compare only quality.
Thank you.
Okay, so we are finished? Yes. Okay, but anyway, from my opinion, we have to see very interesting presentations where the NMR, especially NMR relaxation, was shown in all details. And please read literature.
Thank you.
It's very useful for young generations. Thank you very much.
Hi.